All right, so we are going to talk about the cubic parent function. And so just like the quadratic parent function is the most boring quadratic function you can have, x squared, the cubic function is the most boring cubic function. So the parent function would be f of x equals x cubed. Okay, so instead of x squared, we are now working with x cubed. Okay, we do have a standard form for cubic functions, just like for quadratics, we have that ax squared plus bx plus c. Same for cubics. It would be ax cubed plus bx squared plus cx plus d. We'll get to the standard form later. Today we're just talking about the parent function and the transformation form. So in proper form, we would have an A value for the vertical stretch, vertical compression, all of that stuff. We would have parentheses. We would have a B value for horizontal stretches, horizontal compressions, and like reflections across the y-axis. Another set of parentheses, X minus C, close the parentheses, put the cube, plus D. Okay, so there's always a minus sign when you're inside the parentheses with x. So if it moves right 7, I would see x minus 7 here in these parentheses. The c value would be 7. Okay, and so we're going to graph some points on our parent function just to see what this function is looking like. We did this in unit 1, but I do want to remind you. So if I plug in x equals 0, 0 cubed would give me 0. If I plug in 1, 1 cubed would give me 1. If I plug in 2, 2 cubed would give me 8. And so we have the point 1, 1 and 2, 8 up here. And so it's kind of looking like quadratic with that curve, only it's a little bit steeper of a curve because we're cubing it instead of squaring it. The other difference is if I plug in -1, -1 cubed is still negative. -1 times -1 is +1 times another -1 would get you right back to -1. And so we have the point -1, -1, and we have the point -2, -8 for the same reason. Now we don't have all positives, we have the negative outputs again. And so it ends up making this S shape. And so this point in the middle where it changes concavity, when we were talking about quadratics, we had a happy parabola. That's considered concave up. If you have a sad parabola, it's concave down. And so right here where we have this concave up piece merged with a concave down piece, that's called an inflection point. Okay? And so where it changes concavity is called the inflection point. We talk about like voice inflection when you like change your voice. So inflection point. And so that's what that means right here is inflection. Okay, the inflection point is also the point of rotational symmetry, because now instead of an axis of symmetry, if I were to draw an axis right down the middle like I would for a quadratic, it is not symmetrical, okay? But if I were to rotate it, do you see how it's the exact same function? And so we have rotational symmetry instead of an axis of symmetry this time. And so where it says symmetry, I want you to say rotational symmetry. And we say about a point, about 0, 0. So the inflection point equals the point of symmetry. So this time when a test question asks you for the symmetry, you're not going to be putting x equals like you were with the axis of symmetry. You're going to be putting the ordered pair, the inflection point. Okay. And so the x-intercept and y-intercept is this point 0, 0 because we haven't moved it left or right, but we will in the next lesson calculate the x and y intercept for when it's been moved. Okay, so for now it's just 0, 0, and 0, 0, because that's the only x and y intercept. But we do find our x and y intercepts the same way we do for quadratic. Plug in 0 for x, plug in 0 for y, and so we'll do that. The other different part about this function from quadratic is now both domain and range are all real numbers. So let those be the easiest test questions for you. Domain and range, all real numbers all the time, because it's making this S shape. Goes forever to the left, forever to the right, goes forever up and forever down. So all real numbers all the time. Okay, and then for max and min, we are going to be finding max and min on given intervals, just like we did for absolute value. But for just the parent function, if I don't limit the domain to a specific interval, they don't exist. So just write D and E for does not exist, because both domain and range are all real numbers. Okay, and so some vocabulary that we're going to be using a lot for this is increasing and decreasing. And so increasing means the function gets larger as you go to the right. And so the way I tell if something is increasing, I think of a positive slope versus a negative slope. Okay, and so positive is going up the mountain, negative is going down the mountain. And so look at these 3 points. They're always going to be collinear with the inflection point. And so if you were to draw a line, let me find, let's use this highlighter. If you were to draw a line between the 3 points, it would be a positive slope. And so this is an increasing function. If I had a backwards, if I reflected this function across the y-axis, and it was this backwards looking S, this function would be decreasing. Because if you draw a line between the 3 points, it's decreasing. And that will be very important next lesson when we're trying to find max and min on intervals. Knowing whether the function is increasing or decreasing is going to be a shortcut for you. Okay, let me see how